you have a spin chain with local interactions that we can just take to be projectors, because I care about frustration-free condition. So there are d states per site. We all know what d is, right? D equals 2s plus 1, so it's the number of spin states. So the local Hilbert space is CD. All right, so there's a CD here everywhere. And we fix the rank of pi jj plus 1 to be r, okay? Which, for non-trivial projectors is less than d squared, right? And you ask, well, suppose pi jj plus 1s are generic. So you have generic projectors of some fixed rank. So each one of them, it could be translationally invariant and generic, but let's say not. Suppose, pi 1, 2 is some rank, some rank r projector, and it's generic. And you ask, well, what is the frustration-free condition? So for what rank and d is the chain frustration-free? How many people don't know what the frustration-freeness condition is? Okay, so what it means is, suppose psi is the ground state of H, and it has to be so this is the ground state. Pi's are positive, so the smallest eigenvalue you can have is 0. And if this is the case, then hjj plus 1 psi is also 0 for all j. Then we say the chain is frustration-free, and psi is the frustration-free ground state. Oh, I'm sorry, yeah, pi. Yeah, I'm very jet-lagged. This is pi. Okay, so the local term. So the global ground state also locally minimizes the energy. So this is like the quantum version of, if you have like a antiferromagnet, you want the ground state to be like this. And if you have on a line, it's like this. And globally, you look at it, it's alternating. But if you put it on a triangle, these guys, anti-align, but this one won't know, because if it anti-aligns with this, it'll align with that, and vice versa. So it's frustrated, right? So this is the quantum version of that. Huh? What about Ising one? Well, it depends on whether the coupling is positive or negative, right? If the coupling is positive, they want to do this to minimize energy. And if you put it on a triangular lattice, classically, that'd be frustrated. But on a square lattice, it'll be frustration-free. Okay? So, all right, so fine. So this can be answered. The answer is, so the question first. The question is, when is H frustration-free, and what is the ground state degeneracy? So what is the dimension of the kernel of H? The weights are 1, but you can put any positive weight and it won't change the ground subspace property. Right? Because, psi will annihilate them. So what I mean is if I do this, nothing will change, right? But let's keep on 1 for now, all right? Not that it matters, but I just don't want to complicate things.
Sorry, what is the second question?
Yeah, so what is the ground state degeneracy, or equivalently, so what I have in mind, what is the dimension of kernel of H? Okay? These have been answered. But first I wanted to tell you what has been answered, all right? And the answer is the following. So R, D, this is R equal D. This is R equal D squared over 4. So here, it's frustration-free, and the dimension of the kernel, the ground state degeneracy is exponentially large in n. Okay? So okay? So, and algebraically, this means as long as, or I should say maybe the maximum of d and d squared over 4, then as long as the rank is smaller than that, then the chain is frustration free and you have exponentially many ground states, okay? Now, it's easy to show that if R is less than or equal to D, so these bounds, so D equals 4 is really key, right? D equals 4 is the point that these two intersect. R equals D and D squared over 4. And if R is less than or equal to D, you can show, there exist product states among these many ground states. You can actually construct product state ground states. The rank is so low, so dilute, you can actually build ground states of the product states. Now this is the open question. Open question is, so we believe, so conjecture. No, actually, I'm not sure I believe it anymore. So the question is, are all the ground states, all of the exponentially many ground states in the regime R less than or equal to D squared over 4 and D, so let's take D to be greater than or equal to 4 so we don't get tangled in what this inequality means. Are all the ground states in this regime highly entangled? What do I mean by highly entangled? I mean, if you were to do a Schmidt decomposition, the Schmidt rank would be exponentially large for any given ground state. If you were to build a matrix product state solution, the matrices around the middle of the chain would have exponential size. So in a Schmidt rank sense, it's easy to show that there are some ground states that are highly entangled. But that's not too surprising, right? If you have exponentially many ground states, there's some very simple algebraic geometry type of arguments, parameter counting, that shows you, you have very highly entangled solutions among the exponentially many ground states. But we want to show something much stronger, and that is they all are highly entangled. Sure. Bipartite. But yes. Say in the middle. Say in the middle. And then you look at the, every one of the ground states, can you prove that each one is highly entangled? So any ground state is highly entangled. Right, so
you could get some form which then what eigenstate. Because I is always 1 plus because it's 0, 1.
So D, the local Hilbert space dimension, D is general, so it's not just 2. And you can have generalized Paulis, I understand, that span the space.
It depends on eigenvalues. Eigenvalues P is 0, 1.
Always.
And the other is plus 1 minus 1. So it's just
Yeah, you can write add 1 and divide by 2, and yeah. I'm not sure that's going to help us. It'll just rewrite the problem, but you can just think of them as projectors. So a pi j plus 1, you can think of it as v of p, j plus 1, and p goes from 1 to r, and v's are orthonormal. So that's like a rank R projector. And yes, you can write it in other bases or whatever. Okay? So is this all I want to say? That's all I want to say about this problem. Oh, so how can you prove such a thing? So I can tell you how you can prove such a thing. Find one example. To construct one example, one explicit construction of pi jj plus 1s that is in this regime and for which you can prove that the Schmidt rank, say, in the middle is exponentially large with probability 1. Okay? And that's enough, because then you can come up with some, genericity argument and say that holds with full measure. All right? Yeah, yeah, these are like standard genericity arguments, right? You want to show something that holds with full measure. You show that there's an example and there's a dense open neighborhood around it, and that proves that what you just showed for that example is of probability 1. Okay, so this is the crisp question. Then I have, since you asked me, I'm going to ask a vaguer question unrelated to this. And so this is really like me asking for help, all right? So can I move on? Any questions on this? Okay. Sorry, can you repeat from beginning? I missed. Fail? Oh, I see. If R is bigger than d squared over 4, actually with a student, we could show that like for sufficiently large d, like d equals 8, then generically it fails. But it can fail. Like it could be that you cannot find one state that is annihilated by all the projectors. I mean, it's not at all strange. Frustration freeness is something special. Like the global ground state doesn't have to be the ground state of all of the interacting terms. Right. If it's a ground state with 0 energy, it's frustration free if it's also the 0 energy of every one of the local terms. No? What's confusing? Is No, yes, true, but that is true. And the sum of positive operators may have a non-zero eigenvalue. I mean, its lowest energy may not be 0.
But what you have written down is with 0, right?
Well, if it's a 0 energy ground state, and then it's frustration free, and then the ground state degeneracy is that. So maybe is this what you're asking? You're saying if it's a 0 energy state, it has to annihilate every one of the local projectors? Yes. Right. If that's the confusion. But you could have a side that's a ground state that has a non-zero energy, right? But then once it's a 0 energy ground state, you can ask the question of how many of them are there? It turns out there's exponentially many of them. It's a solution of some recursion relation, and then you ask how entangled are they? Does that make sense, or it's better? Okay. Sorry, I wasn't understanding your question, I guess. Any other questions? Okay, so one last very open-ended question. So suppose you have a matrix that varies with a parameter t, and it's always real. Okay, so every entry evolves with time. Time is a real parameter t, and it's always real, and it's not necessarily symmetric. Okay. Now, for such a matrix, what do we know about its eigenvalues? Any non-real eigenvalue has to come in complex conjugate pairs, right? Because the matrix is real. So you either have a lambda I that is also a function of time that is real, or if lambda I is an eigenvalue, well, so is lambda I bar. Okay. Now I understand the eigenvalues of So the question is this: do you care? Is there any particular example you can think of where the evolution of the eigenvalues under such a setting is relevant or important? You would think, it's fairly general, but is there an example, like from open quantum systems or what have you? I understand the spectral dynamics of such matrices well. For example, I can show complex conjugates attract. And eigenvalues with small imaginary parts are fairly unstable. And I just would love to find more applications for it. So if anybody has any ideas, or now or later, I'll be happy to discuss. Anything obvious that comes to anybody's mind? Really? Okay. All right. Huh? Okay. And how? What do you have in?
Just if you think, I mean, we are talking about the evolution of eigenvalues, then bifurcation theory deals with it. I don't know if
I see. Yeah. If you think of like so if you think of differential equations and M of t is your matrix, then the solutions are in this exponential form, and they can change behavior depending on whether an eigenvalue has, positive imaginary, negative imaginary, or real. The thing is that M here is not a constant. It also varies with a function of t. So it's not like separable. It makes it much more difficult. But, it's interesting. Maybe it's something that can be pushed further. Okay. So let me know if you have any ideas.
Hello. Yes, so I'll just mention a bit more explicitly the open problem I mentioned at the end of my talk yesterday. So it's just, okay, so let's take, so I'll mention it first for the classical case, and so this is relatively easy to prove, and the open question is to prove a quantum version of this. Okay, so let's say I take a probability distribution over xy here, and it's relatively easy to show this, and q also, right? So d alpha is the alpha relative entropy, okay. Okay, so and a similar lower bound, minimum over x of alpha py given x equals little x and qy little x. Right, so this is saying that the relative entropy between pxy and qxy, so there is an x contribution of that, and the y contribution is upper bounded and lower bounded by the corresponding maximum and minimum. You see, this is in the same spirit as what I discussed yesterday. You can think of it even what I discussed yesterday as a special case where this q is the identity. Okay? Okay, sure. So the alpha is, okay, I should get this correctly. Let's see, 1 minus, I think alpha minus 1 log the sum over, say, p, q. So p x alpha q x 1 minus alpha. I hope this is, the sign is correct. Okay, good. Okay. So yeah, so I think it would be very interesting to come up with a quantum version of that. Okay, so first there's one difficulty, is that what does it mean to condition on these values of little x? So there's one natural candidate. It's the following. So the question is this. Is it true that, so now you have two density operators, rho xy, sigma xy, and I ask the following question, so alpha 1, the one you prefer, the sandwiched one or pets one, okay, minus d alpha px qx. It's a bit too. Oh, sorry. Yeah, thanks. Rho and sigma.
Wouldn't the measured relative entropy, for example, in the
You mean this could be true directly for the measured relative entropy using this?
this conditioning over x equal to x, you know, it's like you do a measurement and so the measured, I mean, could you possibly get in terms the bounds in terms of measured relative?
Maybe, yes, maybe. Yes, maybe I'll state the version I was thinking about, and then we can discuss. So I was thinking of the following. So maximum over now nu x of the alpha of so rho y given x. So what I mean here by rho y given x is rho xy and then rho x minus half, rho x minus half. Okay, so this is the definition of this operator. Nu x a half, nu x a half. Sorry, sigma y given x, nu x a half. Okay, and a similar lower bound as well. Yeah, this is one candidate. So you see what I presented yesterday is very similar to that in the special case where sigma xy is the identity, except there we had basically an extra system, which is the conditioning system. Okay, so it was not quite, I mean, because sigma xy would be basically the classical case, they would commute. But what we had yesterday is a bit more complicated. We had a z here, and sigma xy was identity on xy tensor, the margin on z of this. Okay, and then we can show something similar to here. The question is this true in general? And the thing is that I don't even know it for alpha equals 1, right? So even for alpha equals 1, the statement of this is unclear in the quantum setting. I mean, you can think of it as variations of all these recoverability bounds. It's similar in spirit at least, but it's not exactly the same. Even though I should mention that for alpha equals 1, this is particularly simple because the min and the max here, it's just an expectation over x, where you take the distribution p. Okay, so yeah, so this is the question. Do you have questions about this? No, it could be something else. I don't have a very specific application in mind, but yeah, it's basically this in spirit, that we want to say here that the relative entropy here, there is the x part and there is the y part, and you can bound it by taking the worst case over the x part here, but the y part is generated in the same way. Yeah, I mean, it came up in several questions that I wanted the bound of this form, but yeah, I can't say I have a very specific form in mind. This seems like a natural one, but yeah, there might be other formulations that are maybe simpler. So, I mean, so you agree that this is basically the same as this, except that here I'm replacing the maximum over x by a maximum over distributions over x, right? So this is the py condition on a specific one, okay? Whereas here, because I mean, I don't have any specific one, but I take any possible distribution. Okay, so I don't know if this kind of answers your question, but it's not completely clear. Yes, it's not complete.
Got that here already, right? I mean, that's kind of the classical one there, isn't it? Not the same as this.
No, this is the same as this. This should be the same. Rho of y.
The joint over the marginal, that gives the condition. In the classical case, that would be.
Yes, but okay, yeah, so it would be, the similar one here would be that you put a distribution on x and you multiply this with the distribution. Yeah, this is what I mentioned. Yeah.
Okay, I actually have two problems. One is easy and the other is hard. So here's the easy one.
Why did you do the easy one?
It's also hard. I mean, it's open, but it's easy. This is a quantum channel. It's a generalization of the depolarizing channel. It's got just Krauss operators x, y, and z. No. Pardon?
I can't read what you brought. You want me to?
0, 1, 2, 3. And then it goes identity x, y, z. Yeah. Okay, so this is a channel, and there's something called the coherent information, which is the maximum overall inputs to the channel of the entropy of the output of the channel. Did someone take the eraser? No. Oh, thank you. Okay, I'll just write it like this. It's the maximum over all states psi a prime of entropy of B minus entropy of AB. Okay, and we know what this is actually. It's 1 minus the entropy of the classical probabilities.
Channel goes from A to B.
Huh?
Channel goes from A to B.
Yeah, it goes from A to B. Except, actually, nobody ever showed that. You know, we kind of assumed it was in this old paper by Bennett, DiVincenzo, Smolin, and Wooters. It's because it's really long, but it turns out it's not in there. But numerically, it's true. So you may look at this and say, well, I can do that optimization. I'll just use some Lagrange multipliers. And maybe you can. But if you try it naively, you get frustrated. So I invite you to try this.
I'm sorry, is this a qubit channel?
Yes, just a qubit.
Okay, so you say like numerically this
Hmm?
this thing is numerically very high.
Oh, it's absolutely true. There's just no proof that I know. I mean, fine. So this is that's the easy one. The second one, I want a pair of channels. We'll call them N1 and N2. And it's important that they're not entanglement breaking. However, they are to have the following property. No matter what state you put into them, the tensor product of them, that thing comes out separable. You can call it square root of entanglement breaking, maybe. Okay. Why do I want these? Because this property implies that the minimum output entropy of the channels is additive. And I like it when things are additive. And I even have a proposal for what they should be. We'll let each channel just act with a random isometry. Let's let it be d-dimensional input, d-dimensional output, and the environment's going to be a little bigger. It's going to be d to the sum alpha for alpha between 1 and 2. We're going to choose those independently, and I hope, expect, but cannot show, that with high probability for alpha sort of on the 2 end, that a pair of randomly chosen channels are going to satisfy this property. Why? Well, if I take any pair of such channels, N1 and N2, can you see the bottom of the board? Okay. And I apply it to some state. This is a mixture over, it's a d by d state. And it's a mixture over actually d to the 2 alpha d by d states that are pretty random looking. If they were totally random, we'd be happy with alpha equals 3/2, then this would be about d cubed, and you'd be able to show that this thing was close enough to the identity to be in the separable ball of d by d states. However, this is sufficiently non-random that the state's not going to be in that separable ball with high probability. But it's still a darn large number of states to mix, and actually we could go all the way up to, well, bigger as you like. You just have to make sure you don't make the number of Krauss operators so big that they make just one of the channels separable. And this is a question about probabilities in quantum information, which is the topic of the workshop. Therefore, it is relevant. If you have any ideas on any of this, delighted to know.
Wait, sorry, for the first one, it's like the mass of that or 0?
Pardon?
For the first one, it's the mass of that or 0?
Yes.
For the second one, you want just any pair?
Yeah, yeah, why not?
You can take a 4 by 2 dimensional, take a channel that goes, a PBT channel that goes from 4. Then you take a PBT channel that goes from 4 to 2 dimensions, where the line exists, and now you take 2 copies.
Hmm?
And the output is still PBT. All input states. By 2, so take the Hornetsky.
Yeah, yeah. Okay, then the only...
So there are pairs of channels that have this property. They're called entanglement annihilating channels. Yeah, they call it entanglement annihilating. It's related to this PBT square conjecture also. Somehow.
Okay. Anyone else? Yeah, but I want this one. Can you... extra points? Okay, yeah. No, but... well, that's very nice then. Actually, it sounds like you can then bootstrap to arbitrary numbers of copies and get additivity of The regularized one, right? What's an entanglement annihilating channel? Ah, wonderful.
Thanks, Graham. Okay, great. Neela, do you want to finish off? You're the last person. I'll
Yeah, well, don't worry, don't worry. Yeah, you can use that. I'm so short. So this is a question that is an offshoot of some work that Eric and I did. So I'll state the question straight away. You all saw the alpha Renyi entropy appearing in a couple of talks. Log trace rho to the alpha. And what we want to find is a sharp uniform continuity bound on it. So we are looking for a bound like this. So if we're given two states, say rho and sigma, which are close to each other in, say, trace norm, so half of rho minus is less than equal to some epsilon between 0 and 1, we want to find a tight upper bound on this quantity sigma for alpha greater than 1. Okay? And let me give you a little bit of background. So what is known and where are we stuck? Okay, so so what we did was so let me just state it as a couple of facts. So fact number one is, so if you consider any sigma belonging some density matrix in some Hilbert space, and you consider a ball around sigma of radius epsilon, so let's call this B epsilon of sigma. This is a set of states such that their trace distance with is less than equal to epsilon. So what Eric and I, and independently Jonathan, Michal, and the student proved was there exists a unique state, call it sigma epsilon star, in this ball, epsilon sigma, which satisfies this property that it is measurized by every other state in the ball for all omega belonging to the ball. Okay, so this is fact number one, and so let's call it fact number 1A. And what is this can be explicitly constructed, this state, and if in particular if the state sigma to start with is pure, and let's call it say psi, then the corresponding psi star epsilon looks very much like a state which we saw this morning. So it is of the form epsilon and 1 minus epsilon d. 1 minus, sorry, excuse me, epsilon, yeah, sorry, 1 minus epsilon, epsilon over d minus 1 to epsilon over d minus 1. It's something like this appeared in Benoit Collins' talk this morning. And this is true for any pure state. Okay? Yeah, this is, of course, I meant that. The eigenvalues of psi epsilon star. And then what do we know? So since the psi alpha is Schur concave, you also heard about Schur concavity in the last talk. So what do we know? If it's Schur concave, then rho majorized by omega implies S alpha rho is greater than S alpha omega. So from this we know that this has the maximum entropy in the ball, right? So psi sigma epsilon star is therefore equal to the maximum over of the alpha entropies of any state in this ball. So these things we know, and the last fact here is that we can define a quantity S, well, whatever you want to call it, which is the difference of the maximum value for a state sigma is the difference of this maximum entropy in the state and the state itself. Okay. Okay. So these are 4 useful facts, and now for the last fact, fact number 2, is that if you consider alpha between 0 and 1, In this case, what we can show, or what we showed in our paper, was that this quantity that we considered is Schur convex. And using this fact, you can get a tight upper bound on this quantity for alpha between 0 and 1. And how does that follow? It comes very easily, because if you look at, for example, two states, rho and sigma, which are such that they are close to each other. Yeah? Rho minus sigma 1 is less than equal to epsilon. Okay? And now if you look at S alpha of rho minus S alpha of sigma, this is what you are trying to find, bound. Okay? So let us consider the first case when we want to find a bound on this. So very simply, if you consider the situation when S alpha rho is greater than S alpha sigma, so in this case, this quantity is, so the S alpha rho minus S alpha sigma in this case is, what is it? It's bounded by S alpha rho minus S alpha sigma, because it's bigger, trivial statement. And this is, of course, less than equal to the maximum over all omega belonging to a ball around sigma of S alpha omega minus S alpha sigma. Hope I haven't lost you. Yeah? Because you always have to have the constraint that they are less than equal to epsilon. Okay? But we know that the maximum of this quantity holds for the state S sigma epsilon star. Right? We just showed here that the maximum, I'm just using this property. Yeah? So this is S alpha minus S of sigma. That's this quantity. And this is exactly the quantity which we call delta alpha star epsilon of sigma. Okay? And this is one direction. On the other side, if you have the other situation where S alpha sigma is greater than equal to S alpha rho, then what do you have? You have the same thing by symmetry, but with instead of sigma, you have rho appearing. Okay? So straight away we have a bound that S alpha rho minus S alpha sigma for any pair of states which are close together in trace norm is therefore less than equal to the maximum of these two quantities of delta alpha epsilon star of sigma and delta alpha epsilon star of rho. Yeah? And but how do we proceed from here? But we know that, Eric, help. From this point, yeah. So we then, we want a uniform bound. You take delta alpha epsilon star of some omega for all possible states omega, right? And then you see we are done because we know that any state, any pure state majorizes every other state, right? And so this is equal to S of alpha of a pure state major star minus S alpha of psi for any pure state. But this quantity is 0, and so you get immediately an upper bound which you can compute because you know what that state psi alpha star is. So what is the question? It's 5 o'clock, so let me just stop by saying that for alpha greater than 1, unfortunately, this alpha epsilon star is not Schur convex. So this thing doesn't work. So one needs a new idea. So you replace, so the fact is that here what we get is actually stronger than the funness. Here if we take the limit alpha going to 1, then we get back the out-and-out funness. So but you're saying bound the S alphas by the normal von Neumann?
No, well, if you want something stronger than funness, I guess.
No, funness is tight. So for, you can't get stronger than funness, but this is for the alpha. Right. So what we get here for alpha between 0 and 1 is tight, and we can, in the limit, retrieve it. But it would have some nice applications too. according to, Steve Flamia, there might be some applications in proving Hastings' proof of some area law, where he uses continuity bounds for the alpha Renyi for alpha greater than 1, which can be simplified. But anyway, it is interesting open question. We can do the alpha between 0 and 1 in a very sweet way using this shear convexity, but we don't know how to do it for alpha greater than 1. So let us know if you have any thoughts. Sorry for overrunning. It didn't take too long, though.